very peaceful here. Well, it's been about 4 years since I made a video. There was a hawk. I've been busy, you know, things got in the way, good things, raising kids, building a house, writing a novel, that sort of stuff. You know, run of the mill, really. But now I'm back making videos, and I think I want to finish the series on Hawking radiation. And I think I will continue, I think the next video, well, this video, this is just an intro. I will start with something simple, well, rather I will continue with something simple as a way of warming up, and then we'll progressively get there after a few videos. Lots of mosquitoes here. Yeah, so I just want to say hey, welcome back to my channel if you're still here. Noticed a lot of new subscribers, relatively many, I would say, considering I haven't been making videos, so thanks for that. And yeah, enjoy this video. Cheers. So what I'd like to do in this video is to discuss particle creation in a time-dependent metric. In one of my previous videos, the one on the Unruh effect, we have seen that observers moving with a constant acceleration see particles in what is a vacuum state for inertial observers. But the spacetime in this scenario remained flat. Now let's look at an example where the spacetime is conformally flat but is changing with time. Conformally flat means that a metric can be cast into a form that preserves angles but not necessarily lengths. A good example of such a metric is the Friedmann-Lemaitre-Robertson-Walker metric. For simplicity, we will work in 2 dimensions only. A here is some arbitrary real function of time. To see that this metric is conformally flat, all we have to do is define a new time parameter, eta. Plugging this expression back into dt, we obtain a metric that does indeed preserve angles. We can also define a new function a tilde, which is just the function a expressed in terms of eta. Now that we have this conformally flat metric, we need to write down the correct Lagrangian for the field. Recall what the Lagrangian of a field with mass m was in flat spacetime. I covered this in my video on quantum field theory. This term is just this, since eta is the flat spacetime metric, not to be confused with this eta. It won't surprise you that the correct Lagrangian for a general metric is one where the flat metric eta is replaced by g, which by convention denotes an arbitrary metric. This way the terms in the parentheses are invariant under any coordinate transformation. This factor here ensures that the spacetime volume is also invariant. Let's check that it does. The volume transforms like this, where J is the Jacobian. And we know how the metric transforms. The determinant of G prime is the product of determinants of these 3 matrices. This is just a theorem. Notice that these matrices are just the inverse of the Jacobian. So this factor here, when expressed in the prime coordinates, reads. Another theorem regarding determinants says that the determinant of any inverse matrix equals the inverse determinant of that matrix. So this factor here is just 1. So indeed, this volume factor is invariant. The reason for the minus sign is that the determinant of any spacetime metric is negative. So we have to counter that with a minus. Okay, so what is the Lagrangian for this metric? Well, all we have to do is plug in the inverse metric and the metric determinant. So the effect of time dependence in the metric is that the effective mass becomes time dependent. We will see in a minute that this term in fact is what leads to particle creation. To see this, let's consider a simple example where a tilde is a constant at eta equals to plus and minus infinity. We can set a tilde squared at minus infinity to 1. That way we start with spacetime that is flat, since eta equals to t in this region. And let's call a tilde at the other end a naught for simplicity. Here the metric has the factor of a tilde naught. In fact, let's simplify this function even more by making this transition instantaneous. The Euler-Lagrange equations for this Lagrangian with an arbitrary a tilde is this, which is of course the Klein-Gordon equation for a time-dependent mass. We can solve this equation easily in the two regions where eta is negative and positive, since a tilde is constant in both. The solutions are plane waves, but with different frequencies. The most general solution for phi, which is a real scalar field, is an integral over the plane waves and their complex conjugates. The a and a dagger are operators that must obey this commutation relation, so as to make this commutation relation satisfied. Now, we can do the same thing on the right-hand side, can't we? The only difference is that the particles on this side have a different mass. The A operator defines a vacuum, and the expectation of the number operator is 0 on both sides. So where is the particle creation I've promised? Well, first we need to solve this equation correctly. Yes, it is true that this function is a solution, but it's not the correct solution for the initial condition, which is this. The phi on the right must match the phi on the left at eta equals to 0. If we plug in the solutions from the previous slide, we see that they do not match, because these factors are different. To find a solution that does satisfy the initial condition, we can try replacing the positive and negative frequency waves with a linear combination of the two. Plugging this into the phi on the right, we see that at eta equals to 0, the initial conditions are satisfied if alpha plus beta equal the square root of this ratio. However, we must also satisfy this commutation relation, which can only be done if alpha squared minus beta squared equals to 1. I will let you prove this as an exercise. Also, I will skip the simple algebra of solving these sets of equations. You can check yourselves that the solution is this. Let's go back to the field operator and group the exponential terms together. Now the field operator on the right-hand side looks the same as the field operator on the left-hand side. But these operators are different. Let's call them B and B dagger. This linear transformation is called Bogolyubov transformation. Since these operators satisfy these commutation relations, we can define the lowest energy state, the vacuum state, as we did for the A operators. The expectation value of the number operator is 0 for the B vacuum. However, it is not 0 for the A vacuum. The function beta squared looks like this. The integral can be evaluated exactly, but the expression is quite complicated. Let's instead look at the limit of large A. This is how many particles were created by the sudden change in the metric. Now, you might be asking, why did we choose to take the expectation of this number operator using the A vacuum? Wouldn't the observers living in the new metric observe the new vacuum, the B vacuum? The answer is no. And the reason is very simple. Whether you realized it or not, we have been working in the Heisenberg picture the whole time. You can do a quick check to see that phi is in fact a solution to the Heisenberg equation of motion, as well as the Klein-Gordon equation. And in the Heisenberg picture, it is the operators that evolve, not the states. So if you start with a certain initial state, which in our case is the A vacuum, you will end up with the same state. It does not change. So there it is, a simple example of particle creation from a time-dependent metric. I don't know yet what the next video will be, whether I will jump straight into Hawking radiation. It is a rather complex subject and I would like to simplify it as much as possible, so I have to give it some thought as to how I'm going to do that. But there will definitely be another video soon.